Okay, let's get started. Good afternoon, everybody. I'm Tulip from the University of Washington, and like Sue said, I'm going to talk about a new tool we've developed at the University of Washington to locate performance problems along internet paths. So let me start my talk with a very simple question. If given a problem path, let's say from that laptop to that server-looking box over there, and I'm talking about problems such as packet loss, high queuing, or significant reordering along the path, what would you do to figure out where exactly along that path the problem is? I'll come to the limitations of existing possible tools that you might use and what the problems with those are, but you might call your provider or ISP if you have one, and you know what they're going to say, the problem is elsewhere. And beyond that, you have no way of figuring out where the problem is exactly along the path. So I'm going to try and fix this situation by telling you guys about a new tool that we've written, and that fixes some of these problems here. So a very brief slide on what the limitations of existing tools are. The first is, like, if you are an operator and not like an end user like me, you might think of using SNMP stats to figure out where the problem is. The problem with SNMP stats is that, well, you have access to only your router. So you can collect them only inside your domain. And if the problem is elsewhere, SNMP is not going to help you figure out where the problem is. And then there are granularity issues with SNMP. You can't tell where packets from a particular flow are being lost or queued. You can tell something in the aggregate. So if the problem is really widespread and affecting everybody, maybe SNMP can help you deal with it, but not otherwise. You might think of using ping and traceroute like tools, but the problem with them is they measure the round-trip path to the router and not the forward path. So here's an example path, the same path as on the last slide, and the problem is on the second link. And those wiggly arrows on the bottom basically show the path back from the router, which is not the same as path to the router, which is like the common property of the internet, that paths to and from the destination might not be the same. So what ping does, suppose you're using a ping-like tool to do a hop-by-hop localization of the problem. So you measure to the first router, find that the path is clean, so the first link along the path should be clean. But now you measure to the second router. The fact is the forward path to the second router is clean, but the reverse unknown path has some problems on it. So ping might basically make an incorrect inference here that the second link is lossy. But in fact, when in this particular path, the third link is lossy or some other problem along it. So in summary, then the problems with ping and traceroute like tools that measure round-trip paths to the routers is basically that they conflate the properties of the forward and the reverse path. And this is kind of makes the fact that there's path asymmetry in the internet, it makes it worse because the reverse path is unknown and you don't know what you're measuring when you use ping then. So here's an overview of Tulip. So what Tulip does, it localizes reordering, queuing, and loss along internet paths. It works just like ping and traceroute. Run it from a host to any arbitrary IP address. And here's how it works. Instead of measuring round-trip paths to the router, it measures the forward path. And how it measures the forward path only without measuring the reverse path, I'll get to in a minute, but it measures the forward path to the router. So if I wanted to know what's happening on the second link, I'll measure the path to the second router and the first router and subtract the properties. So if I see, so I'm measuring the forward path to the second router, and if I see losses, and I measure the forward path to the first router where there are no losses, I know the fault is probably on the second link here. Similarly, for the third link, measure the path to the two routers that surround the link, only the forward path, mind you, and you know what's going on here. So basically what Tulip does is measure the forward path to the routers and uses that as a basic building block to figure out what's happening on the forward path from where it's running to an arbitrary destination. And how it measures the forward path is basically it uses ICMP timestamps and IP identifiers to figure out the paths. And I'm going to talk about both of these in the next two slides. So here's what Tulip does for queuing along the forward path. It uses ICMP timestamps to access the router clock. So to the router, it sends an ICMP timestamp request and gets back a reply, which is the router's local time. This is not synchronized. These clocks are not synchronized by any means. Like the clock on my host where I'm running Tulip and the router are not synchronized. But thankfully, we don't need synchronized clocks at all. For the following reason, that we are actually inferring queuing from the variation in the delay. So all I need is like how much the difference in the times my probes take to reach the router, and which is basically just a simple counter implemented at the router, and that's good enough to infer delay variation. And there's some amount of engineering required to make this work. We have to calibrate the clocks at the router along with that of the from the probing host, basically, because the router clock might be progressing at a different speed. And then we have to take into account the router might also take some time generating the response back. So after you've dealt with this level of engineering, what you have is basically one-way delay variation to the router, which is, in most cases, should be good enough to infer queuing on the forward path to the router. Now, if you're going to pay attention to one slide in this talk, this is the one. This is the coolest trick, the one I really like, measuring the loss on the forward path without being confused about what's happening on the reverse path. So we use the IP identifier field here. And IP identifier field, as most of us know, is basically a special field in the IP packets. Initially, they were put in to enable fragmentation and detection of unique packets in the internet. And in most routers and end hosts on the internet, this IP ID is implemented as a counter. So keep in mind, we have access to this one counter, and I'm going to show you how we can use this counter to infer loss on the forward path. Send 3 probes to a router. Let me call the first and the third probe as the control probe, and the middle one as the data probe. And I'm interested in measuring the loss only of the data probe and not of the control probe. If there are no losses in any direction, what I get back is basically the IP identifiers that the router puts in. So in this case, ID1, ID plus 1, ID plus 2 here. Keep that the routers and end hosts, they generate a new IP ID counter only when they generate a packet, not when they forward. So in most routers in the internet, this counter is not moving very fast and is actually very useful to get this thing going. So imagine now what happens if the data packet gets lost on the forward path and both the control probes actually reach the router. So what you get basically is ID and ID plus 1. So in this particular case, unambiguously, we know that the data packet was lost on the forward path because we got consecutive IP IDs back. Hence, the router could not have generated any other packet in between generating ID and ID plus 1. The problem is here. What if we did not get a response back to the data packets, but only got back, ID and ID plus K, where K is more than 1, so non-consecutive IP IDs. This is a case where the direction of loss is basically ambiguous because we don't know whether this happened and the fact that our control probes did not reach the router close enough in time, or this could have happened, that the data probe actually reached the router but but the response did not make it back. So in this particular case, Tulip cannot tell in which direction the packet was lost. Fortunately, this does not happen that often. So when this happens, it's kind of indicative of that the loss is on the reverse path, but it's still ambiguous. But on the other hand, when the loss actually happens on the forward path, there is a case which happens often enough that you can tell the loss happened on the forward path and not the reverse. And another thing I noticed in my measurements was that the problem with measuring to a router is you don't know what you're seeing, especially when measuring losses, is whether what you're seeing is impact of rate limiting of responses at the router, or you're actually seeing path level losses on there. So where this 3-packet technique that Tulip uses actually helps us, if response rate limiting is being implemented at the router, if one of the probes get lost, probably the other two would also, or if the second probe, if the probe in which we are interested in gets lost, the chances are the third will also get lost. So our control probe also gets lost, in which case Tulip fails to make an inference, but will not make an incorrect inference and confuse response rate limiting and loss on the forward path. Okay, now that I've told you in some detail about the losses and stuff, there's a pop quiz for you. You can keep working while listening to the talk, and which I'm not going to go into. What is the basic building block for measuring reordering? Remember that we have IP ID counters at the routers, and we can use that to measure reordering. And I'm going to leave that one for you guys here. Okay, implementation. Tulip is implemented in Ruby on top of script route. My colleague Neil Spring was here, I think 2 nanogs ago, talking about script route, a very basic but flexible internet measurement tool, and it runs on wherever script route would basically run, Linux, FreeBSD, and OS X. It runs in 3 phases. In the first phase, given any destination to probe to, it discovers routers along the path. In the second phase, it would test the routers which support forward path diagnosis. So not all routers implement IP IDs at counters. Similarly, not all routers have ICMP timestamp requests turned on. And then it measures the paths to those routers, and at the end of its probing in period, it returns properties of both the one-way and the forward and the round-trip paths to the routers. Here's a sample output from the tool. From those of you who can actually read that slide, but let me just say it. So basically, I logged into my machine at University of Washington and measured to my laptop over here. So what this is showing, like the first column is basically the name of the router. very coherent naming scheme. If you see, you can tell where the path is going. And this is the IP here. This is the round trip loss seen along every hop from the probing host. So there's pretty much no loss here. No loss on the forward path and no in the round trip path. And CO is basically how many consecutive IP IDs did I get back, which is kind of a measure of how fast the router's IP ID counter is moving, or whether or not we can actually get Tulip going with that particular router over there. And reordering, Tulip shows our reordering because the correctness in some sense of the loss probe depends on packets not being reordered. There were some assumptions in the way we send triplets that packets get to the router in the same order. And if reordering happens, Tulip can detect that instead of being fooled by that completely. So that's one output. The lines where we do not have any forward column printed is basically routers we cannot measure the forward path to because we could not get consecutive IP IDs from them, or they did not return the probes we send them. So there are a fair number of routers that don't let us measure the forward path to them, but a lot of them actually do. So AT&T is pretty much switched off here, and then ATT-ENS, not sure what that is, but we can measure the forward path here and here. And this path is pretty much clean, except when you come towards the end of it over here, there's actually like loss on the last hop to my router. This is probably the wireless hop, so unsurprisingly, we see about 1.5% loss over here in the round trip path and not much in the forward. I'll have to remind you, the round trip loss rate, the way Tulip measures, could be both on the round trip or the forward, because only the forward direction is unambiguous. But there was a very interesting thing when I was actually running this tool this morning. I started running this tool when the session was not on, and I was seeing very few loss rates. As soon as the session turned on, the loss rate got high on this link. Like, people were working on the laptops more during the talks than outside in the session when everything's open. Okay, this is just, I put in a pretty picture here just because I like this picture. A very similar experiment, what it's showing is from my desktop in Seattle. I measured to all the machines that host Planet Labs. This experiment was done about 3 or 4 months back. All the machines that host Planet Lab, and what I'm showing on the slide here is the paths to various places where I actually saw losses. And the X's there correspond to links where the losses were. And so we see, and these were mainly access links of these universities or something. So going into Stanford, for instance, there was some amount of loss in their access link to the ISP, and which probably is Abilene. And similarly, losses for while going to other places and stuff. And so I pointed out in the beginning that tools like ping, they can give you incorrect answer in presence of reverse path asymmetry. And here's just an example path for that. So the red line is the basically queuing or the delay variation measured using round trip probes by ping. And the blue line, the bottom line, is that of Tulip, which is measuring one-way queuing. So if the measurements taken by ping are consistent with each other, and it's actually measuring the path it's supposed to measure, the queuing it measures to the router should never go down. So on the x-axis is basically the number of hops from the source where the measurement is happening. On the y-axis is the measured queuing. It's basically median queuing delay. So with ping, you see, queuing goes up and then comes back down. And if ping was consistent, this should not be happening. So the blue line is Tulip, where you see it's pretty much consistent and it goes up towards the end of the path. Where you also see the round trip, but there's this whole area, gray area, where ping can actually confuse you what's going on, just because the reverse path is not the same. So apart from implementing, we evaluated it in various ways. We evaluated whether Tulip is accurate or is being confused by all sorts of router idiosyncrasies in the internet. And we did that mainly using end-to-end correctness tests where we could control both ends and not just the probing end, and measured how internally consistent Tulip was. Just like the last experiment, if Tulip is correct, then the loss rate measured along the path should increase along the path and never come down. And I'm not going to go into those experiments, but they are there in a paper. I'll point out a URL towards the end of my talk where you can look at the paper. But I'm going to talk about this another evaluation we did, which is what is the granularity of fault localization Tulip can achieve. So in the example I showed you, a lot of routers did not export the forward path measurement primitives Tulip needs. So we tried to measure that. So just to recap, where does loss in granularity occur from? So imagine this path, where there's some problem along the third link on the path marked by X, and the router that is blacked out, Tulip cannot measure the forward path to the router, either because the router does not support the feature we require, or because probes do not take a prefix path to the router. Mainly, they take a completely different path because, we are sending the path to the router. There's no guarantee that the way the probe will get to the router is actually a subset of the end-to-end path we are interested in. So in those particular cases, Tulip identifies that and cannot measure forward path to the router. So what Tulip would just tell us, it will measure to the first and the third router and would tell us, well, the fault is somewhere between the first and the third router, and I cannot tell you at any more granularity where it is. It's somewhere in the middle over there. So we measured basically thousands of paths from 3 sources, and this is a graph we obtained as to the fault localization granularity. It's about 2 hops for loss on average, and the median is 2 hops for loss, and it's 4 hops for queuing. The reason that granularity of queuing is worse than that for loss is basically for queuing, remember we need ICMP timestamps, so we need to address the router directly. But while measuring loss, we can use TTL limited probes that are addressed to the destination, but their TTL is limited. So they come back midway. The chances of us getting to the router using the same path as taken by the end-to-end probe is higher when using TTL limited probes. And that's the simple reason why we get worse granularity for queuing, even though 90% of the routers we measured to do export ICMP timestamps, but only 70% export IP IDs as counters. So the difference comes from the routing idiosyncrasy in the internet. This, I should point out, is basically a graph if you were doing only forward diagnosis. But in some cases, there is a chance that you can localize the fault even further by doing round-trip probing. So remember in the last example, Tulip was measuring to the first and the third router. Suppose we could measure the round-trip path to the second router, not the forward path only, but the round-trip path. And that path comes out clean. So the good thing about round-trip probing is, if the round-trip probing is clean, that means the forward path is also clean. So in this particular case, if we can measure the round-trip path to the router, we know the fault is actually in the third link and not in the second one. So that is basically where the current status of Tulip is. It kind of works, in our experience it works, and it provides reasonable, useful granularity while diagnosing problems in the internet today. But there are simple things we can do to further improve the granularity of locating problems in the internet if the tool proves useful. First is to just turn on features used by Tulips. If operators keep turning on the ICMP timestamps, even though they can rate limit them, rate limiting will not confuse Tulip, and letting Tulip's loss measurements, for instance, which need a 3-packet burst to go through, and implementing IP IDs as counters. So basically what this would do in a very simple manner, it would let you and other operators diagnose paths through your network without any overhead to you, even when they suspect. So they can just measure and see that you can show them basically your network is clean and the problem is somewhere else. So they'll actually believe you when you say that to your customers, if they can do it themselves. Plus, then beyond that, if Tulip becomes a runaway success, there are very simple changes that we can make to the current infrastructure that would further improve its effectiveness. And I'm going to talk about 2 such changes here. One is just the granularity of localizing queuing. We saw that it's slightly worse than queuing. Sorry, the granularity of queuing is worse than that of loss. So we can improve that a little bit and get to that in the next slide. And the other one deals with how do we increase the effectiveness of loss measurement. So here's the problem that can be solved with a very simple fix. The problem is the following, that ICMP timestamps need to address the router directly. As a result of that, we get reduced diagnosis granularity or localization granularity when the prefix path property, which is the path the probes take to the router, is not a subset of the path to the destination, when this property does not hold. So here's a simple fix to that. Why don't we just insert timestamps in the TTL expired messages themselves? There are 32 unused bits sitting in the TTL expired messages. And if we start inserting timestamps in those 32 bits, what we can do is not only measure loss and queuing using the same probe, but also the fact that we also get much better localization granularity with queuing. And the change is completely backwards compatible, and it can be deployed incrementally. There's no flag days required as such. Here's a second simple change, and here's the problem. And I wonder if it has occurred to any of you when I said IP IDs, basically Tulip uses IP ID. So note that IP ID is a shared counter for a router. So what would happen if all of you sitting here start using Tulip at the same time? Then that counter is basically moving very fast. As a result of that, what we get is a success nightmare. The counter is moving very fast, and Tulip is completely useless then, because nobody can get consecutive IP IDs out of the queuing. So here's a very simple fix to that. Let the router maintain n, where n is a constant number of counters, and the router should basically pick which counter to respond to using the source address and the IP ID of the probe. So even a small n like 10 or 100, this is not per flow state by any means. Like maintain 100 counters instead of picking from one counter. And whenever a probe comes to the router, it should just hash the source address and the IP ID of the probe to select which counter to use and return. And this is completely compliant with the standard in the sense, given a source destination pair, the IP ID still remains unique. And the change, again, like the previous one, is completely backwards compatible and can be deployed incrementally. In fact, you can think of like the current internet implementing the same scheme. It just so happens that n is equal to 1, that everybody hashes to the same counter. So to summarize, I talked about Tulip, a new performance diagnosis tool that we've developed locally. Tulip finds where packets are lost, rerouted, or queued to within 2 to 4 hops on average, depending on what problem you're diagnosing or what exactly the path you're going through. And the biggest feature, the biggest contribution in Tulip compared to the existing tool is that it's completely compatible with asymmetric routing. It measures the forward paths to the routers rather than measuring the round-trip path, as a result of which the diagnosis is more accurate. And the source code of Tulip and packages for Red Hat and Debian sector are available through that website over there. And that's about it. Thanks very much.
Jeff Goodfellow, the Goodfellow Media Group. You mentioned that you used Tulip before and after the sessions here at NANOG, and that you noticed the loss went up during the sessions.
Yeah.
Did you happen to use it during the various sessions to see how the loss rate changed from speaker to speaker?
That's a good idea. Unfortunately, I did not.
We'd love for you to do that sometime.
I should have done that.